Okay, everyone. In this lesson, we're going to study atomic radius for the first time. And you will need to have two papers for this lesson, one of them for your notes and one of them for your classwork. The classwork should include these questions from the Do Now. So you can start there, and there won't be a bookwork associated with this lesson, but we will have a Do Now and a pair up and a summary. So read these questions, copy them down, and we'll answer them in class. Periodic law is the first thing that we'll talk about in this lesson. Periodic law states that the properties of elements on the periodic table vary periodically. So, in other words, this means that certain properties on the periodic table will repeat and then they will sort of restart. So, maybe for instance, we can look at atomic radius, which is one of the things we're going to see today, and the radius of an atom will increase as you move across a certain direction, and then it'll decrease as you go to the next row, for instance, and then the pattern will begin again. So it's this idea of like an increasing property that then sort of stops and restarts, and that's periodic law. So an introduction to periodic law could be approached with this method, where we're going to have a quad for each element, and in the top left corner of the quad we have element symbol, and in the top right corner of the quad we'll have atomic number, electron configuration in the bottom left, and the most common ion charge in the bottom right. You can use your periodic table for this, which is also nice practice. So for instance, if you look up lithium on your periodic table, you'll find that its atomic number is 3, that's the number of protons it has, and its electron configuration is and let's see, the last thing was the most common ion charge. So you can find that under oxidation state, and it's going to be the very first one that's listed. So in this case, it will be positive 1. And then for beryllium, it's atomic number 4, 2, 2, and plus 2. So I think you see how that's working. So please use your periodic table and fill in the rest of these. So I just went ahead and filled in the rest of these, and I was able to show that in addition to lithium having an atomic number of 3, configuration of 2, 1, and a charge of positive 1, I was also able to do that for beryllium, and then boron all the way through argon. And I did them all pretty quickly, and here's what I would point out was my trick. I used the periodic law. And the trick there is that I know that since lithium and sodium are in the same group, they're both in group 1, and that's actually the same for all of these, like beryllium and magnesium are in group 2, boron and aluminum are in group 3, carbon and silicon are in group 4, and I think that you see what I'm getting at there, just going up in order. But if you're two elements in the same group, you will have different atomic numbers. That's just based on your atomic number on the periodic table. But you'll have the same most common ion charge. So elements in group 1 are positive 1. Elements in group 2 are positive 2 for their ion charge. Elements in group 3 are positive 3. In group 4, it switches to negative 4, and that means that they gained 4 electrons. And in group 5, negative 3, they gained 3 electrons. And group 6, they are both going to be negative 2, meaning that they gained 2 electrons. And group 17, or 7, they're going to be negative 1 because they gained 1 electron, and then group 18, 0 because they gained none. And you'll also see similarities in electron configuration. So in group 18, neon ends in an 8 and argon ends in an 8. In group 17, fluorine ends in a 7 and chlorine ends in a 7. For group 16, oxygen ends in a 6 and sulfur ends in a 6. You'll see that pattern throughout the whole set. For instance, boron ends in a 3. This is group 3. and aluminum ends in a 3. So it seems like what group you're in has a strong effect on definitely what the last number is going to be in your electron configuration, but it also seems to have a strong effect on the most common ion charge. Therefore, elements in groups are far more similar than elements in periods, because elements in groups have the same number of electrons in the last electron shell, and they also have the same ion charge. So, atomic radius is the radius of an atom, and it has some fancy definitions too, like the distance from the center of the nucleus to the outermost electron in an orbital, but just think it's the radius of an atom, the same way you would think of the radius of a circle. The subatomic particle that fills the majority of an atom's volume and accounts for the majority of its radius is the electron. So let's answer some of these questions. The distance at which an electron orbits the nucleus is dependent on its nuclear charge. I'm bringing this up because electrons are what makes up the majority of an atom's volume, so that's why we should talk more about electrons if we're going to be talking about the radius of an atom. So the distance at which that electron orbits is dependent on its nuclear charge, and we can use an example of lithium versus neon to help us understand why. So, for instance, between the two elements, lithium versus neon, lithium has a nuclear charge of +3 that's equal to the number of protons in its nucleus, whereas neon has a nuclear charge of +10. It has 10 protons in its nucleus, so greater nuclear charge. Which atom's electrons are more attracted to its nucleus? I would say most definitely neon, and it's a couple of reasons. Remember that electrons will attract protons, which are in the nucleus. And if neon has more protons, then it's going to attract its electrons more. So which atom, therefore, would have a smaller radius? I'm going to say, again, neon. The reason for that is because it has a larger nuclear charge, and therefore it will attract its electrons more, and the electrons will scoot in close to the nucleus because of that attraction, and therefore the radius will be small. So now we can answer a trend question. It says, how does atomic radius change as you move across a period? So as you move across a period, you're moving from elements that are like lithium to elements that are like neon. In other words, as you move from left to right across a period, you'll start with elements that have a low nuclear charge, and you'll end with elements that have a high nuclear charge. Therefore, if you have a higher nuclear charge on the right, you'll also have a smaller radius on the right, and you'll have larger radii on the left. So in short, atomic radius decreases as you move from left to right across a period. So let's talk about how the number of orbitals that the element has might affect the atomic radius. So as a reminder, you know how many orbitals an atom has based on what period it's in. And the number of orbitals changes as you move down a group, because as you move down a group, you add an orbital each time. So since I was just saying that as you move down a group and you add an orbital every time, then you should think about which atom would be a larger atom, an atom that had one orbital or an atom that had two orbitals. So the answer would be an atom that has two orbitals, and it's sort of like a person who would seem rounder, a person wearing one winter jacket or a person wearing two winter jackets. So basically, as you add another layer to the outside, the atom has to become larger. So more orbitals is going to be a larger radius. Therefore, if you put all this together, moving down a group, you add orbitals, and adding orbitals makes the radius larger. So moving down a group, makes the radius larger as you move down the group. But there is a slight dilemma, which is that as you move down the group, going down, you are adding orbitals, so the radius increases, but one other thing that happens is that the number of protons increases. And we were saying on the previous slide that an increase in nuclear charge will make the atom shrink. So if the radii are getting larger as you move down, but the nuclear charge is also increasing, are the atoms shrinking or are the atoms getting larger? So I said, are atoms really getting larger as we move down a group? The answer is yes, and the reason for that is because one of these properties is more important than the other when it comes to determining an atom's radius or an atom's size. As it turns out, the number of orbitals that you have is a much more important factor in the size of the atom. And then it's only when two atoms have the same number of orbitals that the nuclear charge matters. And so I wrote just that. I said nuclear charge matters more between elements with the same number of orbitals. So let's take a closer look at this idea, which is nuclear charge versus number of orbitals, which one matters more. So as you go from left to right within, this looks like period 2, because it starts with lithium and it ends with neon. As you move from left to right, you can see that nuclear charge is increasing from +3 to +10. And what we need to do is estimate the size of those atoms based on their nuclear charges. So I'm a terrible artist in this sense, but within this period, lithium is going to be the largest and neon will be the smallest. And so I just tried to draw them a bit smaller at each succession. And also, the thing you should notice is that beryllium's a bit smaller than lithium, and beryllium's nuclear charge is higher. So as the nuclear charge is increasing from left to right, the atom's radius is getting smaller. So again, this is only appropriate because all of the atoms in this period, they all have the same number of orbitals. They all have 2 orbitals since they're in period 2. So it's only because they have the same number of orbitals that the nuclear charge is determining the radius. But, for instance, when you go from lithium to sodium, look how much sodium's nuclear charge is. It has plus 11, whereas lithium only has +3. So this one has a ton more protons, but instead of the atom being smaller with sodium, the atom is larger. And the reason it's larger is primarily because it has more orbitals. So up here, more protons meant a smaller radius, but down here we have more protons, but we also have more orbitals. Therefore, it's a larger radius. But as you go from sodium over to argon, you should notice a decrease in radius as a result of increasing nuclear charge. So in each example, let's circle the larger atom. You will need your reference table for this. So make sure that you have your reference table, but let's find on your reference table the 2 elements, boron and beryllium. Boron has an element symbol of just a B, whereas beryllium will be Be. And what you'll notice is that boron is just to the right of beryllium, but they're in the same period. So as you go from left to right, the radius decreases. Therefore, boron is smaller than beryllium because boron is to the right. So if I'm choosing the larger atom, I'm going to choose the one on the left, and in this case, that's beryllium. So again, let's do boron versus aluminum. So boron and aluminum are in the same group, meaning that they're in the same column. And boron is above aluminum. Aluminum is below boron. What I know is that as you go down a group, you add orbitals and the radius gets larger. So therefore, my assumption is that aluminum will be larger than boron because aluminum is below boron, and therefore aluminum has an extra orbital and would be a larger atom. When I compare nitrogen versus carbon, I'm looking at 2 elements that are in the same period, but nitrogen is to the right of carbon. So if nitrogen's to the right, then nitrogen will have a smaller radius and carbon will have the larger radius. And when I do chlorine versus fluorine, I'm again looking at two elements that are in the same group, which means that fluorine and chlorine are in the same column. Chlorine is below fluorine, and that means that chlorine would have an extra orbital and it would also have a larger radius. But if I'm trying to compare the radii of boron and chlorine, it's a bit harder. And the reason for that is because boron is in group 13, it's element number 5, and then chlorine is in group 17, it's element 17. But so not only are they in different groups, but they're also in different periods. And this makes it really challenging to say which one's larger exactly. So there is a way around that, and that's to use table S. And table S will tell you the exact radius of any two elements. So when you compare boron to chlorine, I can see on table S that boron's radius is 84 picometers, and chlorine's radius is 100 picometers. So the larger one is chlorine. So I went ahead and recorded that information. And then the next question says, where can you find a listing of each atom's radius to help you settle failures of logic, such as the one above? Use table S. And the next one says, which is bigger, boron or chlorine? So as it turns out, it's chlorine. And what does this mean about the effect on atomic radius of nuclear charge versus the number of orbitals? It means that number of orbitals matters more. So copy down these pair-up questions and this summary question. Just sketch the table. And so you'll have on a separate piece of paper now a do now, a pair-up, and a summary for this lesson, and that goes under classwork in your binder with a date and a title. And you'll also have your notes for this lesson, which will go under notes in your binder with a date and the title.